Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a theoretical physicist currently based at the Helsinki Institute of Physics over in the University of Helsinki in Finland. And I'm a cosmologist, so that means that I study the universe, the contents of the universe, how things evolve, how things interact, a lot of cool stuff happening inside the universe. I love being a physicist, being a scientist. I love getting paid to try to figure out what the universe is made of and what is happening up there. And I love chatting to everybody about all of the cool things I get to study. So that is the purpose of this show. This is an interactive stream. The idea here is that you people can ask me anything you want about science, about physics, about academia, about space, about myself. I may or may not answer those. The idea here is you can ask me anything and I will do my best to answer. Hello to all of the regulars. I see we have Mito, we have Prath, we have one of the Davids, we have Paul, we have Nina over from Mastodon. Great to see all of you joining. For any first-time viewers, welcome. If you haven't done so yet, please do like, leave a comment, subscribe, do all of the usual YouTube things. It really does help boost engagement, and I appreciate each and every one of you who presses the relevant buttons on YouTube and makes stuff happen. Really, very much appreciate it. If you're watching on YouTube, if you're watching on Twitch, wherever you're watching from, feel free to press buttons and chat. I see all the chat messages coming in. Great to see everyone. Scott, great to see you as well. Welcome, everyone. Welcome back to all the regulars. Cool. I feel like I just went very quickly there and did not catch my breath at all at the beginning there, which is probably a good testament of what's going to happen this stream, because I feel like it's just going to be a very hyper stream for some reason. Hey, David Dunn, great to see you as well. Okay, gonna need lots of tea because I'm already coughing, and we're less than 3 minutes in, and I'm already coughing. So maybe we slow things down a bit today. Hey, Ange, great to see you as always. I love Paul's comment here. If you don't recognize a button on YouTube or on Twitch, just press it and see what happens, because that's how we discover things. Also, they keep adding random buttons on the restream side, and I keep pressing random buttons to see what happens, and most of the time nothing happens, but sometimes cool stuff happens. I've now figured out that there's a way for me to actually jump from one image to another without having to go through all of my slide deck, provided I remember which page each of my images are on, which I do not. So there's there's that as well. So I know I was supposed to be on last week. I had said I would be on last week, and then I wasn't. The reason for that, it's twofold. One is because I wanted to go walk in the forest. It was raining. I went for a walk in the forest, and I didn't want to care about getting back home in time. And the other reason is because I had a really busy week and I just wasn't in the mood. And I always have the idea that Cup of Cosmology should never feel like an obligation for any of you viewers, and it should never feel like an obligation for me. And anytime where it does feel like an obligation, I just cancel the stream, because I want Cup of Cosmology to be something that everyone enjoys, myself included. So apologies for not doing the stream last week. Back at it today. And I don't have a topic today. Today is free form. This means that you all get to decide what we talk about. You can ask me anything you want, and based on your questions, we'll move this conversation in one direction or another. That said, I do have a couple of interesting topics coming up, either next week or the week after. I'm going to do a stream entirely about neutrinos, and I love doing neutrinos, so there's going to be a stream dedicated just to neutrinos. I'm planning a stream soon about the Hubble tension, because there may or may not have been some development in that direction. And I want to do a stream soon about the ups and downs of academia, the good, the bad, the messy, the ugly, and everything in between. So I have 3 topics planned for the next few weeks, just not today. Today is chill, ask me whatever you want, and we'll see where we take this conversation. But I do have these interesting streams coming up. I am still, I'll repeat this at the end of the stream, but just saying it now, I'm not completely sure if I'll do a stream next Sunday. The reason being there was a costume party happening at my favorite bar, and the theme is Wild West, and I might choose to go to this costume party over doing a live stream. So follow me on Mastodon or on Mastodon, and I'll let you know if I do a stream or if I don't do a stream. But a general good rule of thumb is I schedule the videos always, like the YouTube live is always scheduled on the Sunday morning, like 6 hours in advance at least. So a couple of hours in advance, you can just check on YouTube, and if there's no upcoming stream listed, then I'm not doing one. If there is, then I am doing one. That's always an easy way to check. And of course, if you subscribe, you'll be notified 30 minutes before I go live. I love David Howden's comment here. If I should just do the streaming costume, like go to the costume party, come back and jump onto the stream, that would be very fun. And it was something that I was thinking about in the past. I had a friend who we were talking about doing a steampunk cup of cosmology, just like both of us dressed in steampunk. And it never materialized, but that would have been very fun. But yes, if I do go to the costume party, I'm not sure if I will then want to jump on a stream, but it would be very funny. I have enough clothes that I can sew together the relevant costume, which makes me question my choice in wardrobe. But yes, if I'm not online next week, it's because I'm at a costume party. YouTube notifies me when you go live, not 30 minutes before. So I'm subscribed to my own channel on a different YouTube account, and I get a notification 30 minutes before and at the time when it goes live. So I get both. I think you can opt into the 30-minute before one, but I at least get both notifications, and I assume that's something that I activated at some point. So you should be able to activate getting a notification 30 minutes before I go live. Do a vlog live stream. Yeah, a live stream directly at the bar in costume. Yeah, then I'd need everyone there to agree as well. So we'll see. If you don't see me next week, it's either because I'm very tired or because I'm at a costume party, both of which are very fun reasons to not do a cup of cosmology, but we will see next week. But in any case, the next stream after today will be a special about neutrinos. Now, very briefly, why am I excited about neutrinos right now? So I have seen there's a question about gravitons. I'm not ignoring that. I will come to that in a sec. But the reason I'm excited about neutrinos now, so neutrinos are these subatomic particles, so tiny, tiny, tiny particles that are traveling throughout the universe. They, Scott's saying here, you usually get the 30-minute one. You're saying on the page it shows if one is scheduled 8 hours ahead, 6 hours ahead, because I manually schedule them on what is my Sunday morning. And I usually schedule them between 6 and 8 hours in advance, depending on basically what else I'm doing Sunday morning. So if you check 4 or 5 hours in advance, if it's not scheduled, it's not happening. So you can always just go to the YouTube channel and check for future streams or live upcoming streams. It should be on the channel homepage. So you go to YouTube at cupofcosmology.com. Sorry, not YouTube at Cup of Cosmology. And there you can always see if there's a live stream scheduled. And I normally schedule it at least 6 hours in advance. So then you can just go and check the page. And if it's not there, it's not going to happen. I've never scheduled one, to my knowledge, less than 6 hours in advance. Okay, yeah, when it is scheduled, it shows up near the top of the YouTube homepage. Exactly, yes, that is a good way to check. And on my side, it is usually no later than 6 hours in advance that it is scheduled. So neutrinos are these tiny, tiny particles that are part of our standard model of particle physics, and they travel freely throughout the universe. Now, neutrinos have several curious things. The first one is they barely interact with anything else. So they don't interact electromagnetically, they interact gravitationally, and they interact via the weak force, but that's kind of it. This means that neutrinos are really difficult to find because they don't interact with much. And neutrinos travel almost at the speed of light, so they're ridiculously fast, not exactly at the speed of light. Now, something that we know is that neutrinos have this weird thing where they can change flavor. They start as one flavor and end up as another. It's like if you buy vanilla ice cream in the shop and when you get home, it's chocolate ice cream. Neutrinos do this. The fact that they do this tells us that they have mass. The fact that they have mass means they do not travel at the speed of light. But here's a cool thing. We don't know how much mass these particles have. We know it must be very small. From a theoretical particle physics perspective, we have two ideas. It should either be this number or this number, but it could be something else. Now, here's why I love neutrinos. Neutrinos is something that we can actually measure using galaxies and using the cosmic microwave background radiation. So how does this work? Well, the idea, I'll go into more detail in the dedicated stream, but basically neutrinos affect how this map looks. So what you can see here is a cosmic microwave background radiation, 10 minutes today. This is the oldest light we have in the universe. This is a snapshot of what the universe looked like 380,000 years after the end of inflation, where you have slightly hot spots and slightly cold spots. Now, depending on how neutrinos behaved in the early universe, this map would look different, and also galaxies would look different. So neutrinos, these tiny, tiny, tiny particles, is something that we can actually try to measure using cosmology. And I think this is fascinating. And it's something that I've worked on a couple of times, but it keeps coming up in my radar. And every time it does, it's like, yes, neutrinos, such a cool topic. And the reason I'm thinking about it right now, and just to answer this question, do all neutrinos travel at the same constant speed, or can some travel slower than others? Now, we don't know exactly how fast neutrinos travel, other than almost at the speed of light, but not quite, because this would be slightly related to the mass that they have, and we don't yet know the mass that they have. So you can also slow down neutrinos in the same way you could slow down photons if you have the right material. So there are things you can do to neutrinos. We don't know exactly how fast neutrinos travel. We say almost at the speed of light, because they are almost at the speed of light, but not completely. And their exact speed will depend a bit on their mass. So this week that's about to start, and next week, I'm attending a remote conference, fully online. It's a really nice format. It's a conference that is actually designed to be online, not just let's all go to a Zoom talk. It's actually a conference really designed around the idea of being online. I've participated in several editions of the bigger conference known as Cosmology from home. And this week that's about to start, and next week I'm participating in Neutrinos from home. And the idea of neutrinos from home is we're getting a lot of experts who work on different aspects of neutrinos, from particle physicists, cosmologists, people working in labs, people who are just working on laptops like me. And we're all coming together to just ask the question of where are we with neutrinos? What are we trying to do? What is happening with neutrinos? It's very, very cool. And something that I personally am super happy about, I was asked to give the overview pedagogical talk on how we measure neutrinos from cosmology, which is really, really cool and very intimidating, because it's a topic I have not worked on as much as some of the other things I work on. But it's a really fascinating topic, and I'm one of the key speaker, giving one of the longer introductory talks. So I'm giving a 45-minute presentation on how we can study neutrinos from cosmology. And the cool thing is the presentation is already done. Because of the format that this conference is completely online, then the talks are pre-recorded. So I actually recorded the talk last weekend, which is another reason I didn't do the stream on Sunday, because I'd lost my voice doing the recording. So I sent off the recording, and it's now been released to all conference participants, and now we have a few days to watch it. And then next week we get together for the discussion sessions. So this means that I'm currently really thinking a lot about neutrinos. I prepared the presentation. I have to prepare for the discussion session in 2 days. So neutrinos are on my mind right now. And obviously I feel like I'm going to learn a lot at the conference, and then I would like to do a stream summarizing everything that I learned at the conference, because I think that would be very, very cool for some people. And no promises, but usually the Cosmology from Home conferences has some outreach events. There's often an Ask Me Anything on Reddit, and occasionally a live stream. I have been in a lot of the live streams from Cosmology from Home. Now, I don't know what is planned for neutrinos from home, but I've seen that there might be some live stream directly from conference participants. Obviously, if that happens, I will advertise it. As soon as I have any info, any details, I will advertise it. But yeah, either this week or next week, this coming week or the week after, there might be a live stream about neutrinos from the conference participants. And then my next live stream, which will either be next Sunday or the one after, depending on costume party, will be entirely about neutrinos, and then I'll go into a lot more detail. Just comment here from Paul. I remember someone once measured them as faster than light, but it turned out to be an error. Yep, that was actually a very cool proof of how science works, because there was one experiment that measured neutrinos traveling faster than the speed of light. And this is something that goes against our general idea that nothing can travel faster than light in a vacuum. Instead of claiming a massive discovery, what the scientists did is they actually just made all of their data and results public. Like, this is what we found. Can someone tell us what's wrong? Or is this actually right? And then there was some analysis, and it actually turned out to be a faulty cable in the experiment. But it was done in a very cool way, where they weren't like, we've broken physics. They were like, Can someone help us figure this out? So yeah, that was very cool. Again, I will go into a lot more detail of all of these questions when we do the stream entirely about neutrinos. Is neutrino mass measured at speed, or do they somehow work backwards to find the rest mass? That's also a question I will shelve until I do the full discussion, because the way we measure neutrino masses is really, really, really cool. But very, very, very briefly, it's related to how galaxies look. And that is cool. You look at galaxies, and based on the amount of galaxies that we have, we figure out how massive neutrinos are. Amazing. Is there a table of contents of the main topics of the old Cup of Cosmology broadcasts? Not an official one, no. I have a spreadsheet somewhere that is updated like once every 3 months, where I just put 2 or 3 keywords of what was covered in each stream. But there is no official table of contents. Now, if that's something that people think could be useful, I could try to set that up. I could have a page, because there is the webpage cupofcosmology.com. There are highlights, and usually if a stream is about one specific topic, then that's in the title of the stream. And I do go back and edit it. Like today, we're doing an Ask Me Anything. If we decide we're going to talk entirely about one specific topic, then afterwards I would edit the title on YouTube so that it reflects what we discussed. But often, because the AMAs, we talk about 5 or 6 different topics, I don't always list that. But if this is something that people think would be a good resource, I could put that together where you could search for like which videos to go to for specific keywords. I feel like that might be a lot of work, but also something that could be very useful to do. So if there is general interest in that, let me know, and I will look into doing that, because I have this spreadsheet that I think has not actually been updated in 2024. I'm not even sure when it was last updated, but I could turn that into an actual like catalog that people could search. It also has all of the HAP streams there, so it goes back a while. You want a table of contents of all the times you've talked about tea? Yeah, that would probably be a very long table of contents. I do like tea. I am a big tea enthusiast. This is not actually tea. This is an infusion this time. It's a berry infusion. And it's pretty decent. It's not one I would buy for myself, but I get a free either tea or coffee or free. I get tea or coffee included with my lunch if I go to the university canteen, which I don't do often because canteen is of not great quality. But they have this okay-ish berry tea, and I always get this berry infusion there, and then that's what I have today. Press, will the conference videos be published online? Probably. I can't guarantee that all of them will be, but this is one of the cool things, that because the talks are pre-recorded, they are currently on YouTube as unlisted videos. I cannot share any links. This is like direct rule of the conference, cannot share anything. But when we submit the video, there's a button we can click of, do you want your video to be public? And it's yes or no. And then usually about 2 or 3 weeks after the conference ends, those of us who said, yes, make my video public, those videos will be made public. So mine will be public. I click the yes, make this public button. They normally take a while because the organizers will check the transcripts and the captions and everything, and then put it online. So yeah, it will at least some of the conference talks will be public, but I don't know how many, and I don't know when. I'm not involved in organizing this conference in any way, but I clicked a button that said, yes, make my talk public after the conference. And in previous Cosmology from Home conferences, it's taken about 2 weeks to get the videos public. So they should be public, but bear in mind that these are aimed at other people who work on neutrino physics. So it's a very, very different way of presenting things than what I do here. Mildly spicy take. I love mildly spicy takes. This is where AI could be helpful. Having a chatbot read your video transcriptions and form a bulleted summary would be so helpful. So I don't, my thoughts on AI. This is something that they actually can already do. I'm not sure, I think it's ChatGPT. It's either ChatGPT or OpenAI, where you can give it a link to a YouTube video and it creates a summary. I'm not sure at what level it does it. I think it's based on actually going through the transcripts and then from the transcript picking out keywords. So this is something that I think already exists, but it's not something that I'm going to do because, as you all know, I'm not a fan of AI in quotation marks, of these glorified algorithms. So it's not something I'm going to endorse in any way, but I do believe that that is something that is out there. Okay, so just wanted to tell you all about this conference. It's a very cool conference that's going to be happening. I'm slightly scared by the fact that the discussion session about my talk is the first one of the conference. Like, we are opening the conference on Tuesday with a discussion about my talk, and it's a 25-minute discussion, and people can ask me anything they want about neutrino physics, and I'm there as a cosmology expert. So that is a bit intimidating because I'm expecting very, very cool but very tough questions. And that is how we open the conference. So that is slightly intimidating, but also I'm really looking forward to it. It's going to be really, really fun. So yeah, you need a broadcast someday to help me know all the different T terms in fusion. You know, I could branch out and do a cup of cosmology. Let's talk about T, and discuss all of those things. That would be a very fun stream. It'd just be me info dumping everything I know about T. Just the big difference here, tea actually has tea leaves in it, and fusion doesn't have any tea leaves in it. So the one that I have here is just basically dried berries that have been like, it just says the berries, but there's no actual tea in it, which is why I make the distinction of tea and infusion. So infusion doesn't have tea in it. If it has tea in it, we call it tea, not infusion. That's the basic difference between tea and infusion. But don't worry, this is not a tea stream for now. Cup of theology, that maybe someday we do maybe at some point. Is there an international tea drinking day? I feel like there should be an international tea drinking day, and then we can do a special of just me talking about my favorite teas, which would be fun. And then, like, I'm going on a tangent here. I recently bought a teapot that is made of glass, and it's just so pretty because I can see the tea brewing inside, and you can actually see the color of the tea, and it is extremely pretty, and it is just such a random detail. But I really like my glass teapot. It's something that has just made me very happy the last couple of weeks. Every time I use it, I'm like, look, I have my, and it's just like a very round, nice, satisfying teapot that is made of glass. And anyway, let's park the tea chat, and then we can come back to a couple of theology at some point. But there was a question. Yes, just comment here from Angela. Then at least it's done and I can enjoy the rest of the conference. Exactly. The advantage of going first at the conference is that then it's done and then I can enjoy the rest. And yeah, then I get it over and done with. It's slightly scary to be opening the conference, but it also makes sense given that I'm giving the review on how we can constrain neutrinos from cosmology. It makes sense that we open the conference with that one. And I did request to be in the early slots, but I saw the timetable on Friday. I was like, oh, okay, let's go. This is going to be fun. So Tuesday, I'm going to be a bit, ooh. Did you have masala chai in India? I did. I had a lot of chai, a lot of masala chai when I was in India. Now, honestly, I am not a huge fan of milk in my tea because I just don't like milk in general. And masala chai or chai in general was served with milk, which is fine. It's just not to my taste. I did enjoy quite a few masala chais, but it was not really to my taste because I generally take my tea black. Okay, we're doing tea from now on for all future episodes. Yeah, we're just going on tangents as always. This stream, it's an ask me anything. Someone asked about tea, we go on a tangent about tea. Actually, I don't think anyone asked. I just started talking about tea, but that also happens. Okay, just want to go back because at some point back before I started talking about costume party and tea and tangents, there were questions about gravitons by Paul. So let's let me go back and find the gravitons questions. Question from Paul with 3 parts. Okay, if gravitons turn out to be true, would that mean 1, space is not curved? 2, gravitons operate within the curved space, or 3, gravitons and curved space are just 2 different ways to explain the same phenomena of gravity? Multiple choice question. Okay, so neutrino tea might be hard to brew. There are neutrinos in my tea at any given time. There are thousands of neutrinos around us in the same way that we have the cosmic microwave background. We have a cosmic neutrino background, which means there are neutrinos around us at any time, everywhere. Cup of Theology, where Diana explains that the universe exists for the purpose of giving us tonic beverages. Yeah, what is the purpose of the universe? Tea and chocolate. You can't go wrong with tea and chocolate. Okay. Indian tea tends to be super milky and super sweet. Yeah, I did enjoy it sometimes of the day, but I feel like I was consuming a lot of milk-based products while I was in India, which made sense, and they were all really delicious. And at some point, I was like, I don't think I can manage more masala chai right now. But it was a good drink. I did find it quite hard to find black coffee when I was in India. At some point, I found black coffee and it was 11 p.m. and every ounce of reason told me it is too late in the day for coffee. But I found black coffee for the first time in a few days, and I downed that coffee and did not sleep. Yeah, chai tea is redundant. It is, except that those neutrinos never get consumed. Well, the neutrinos that are orbiting everywhere around me do not indeed never get consumed because can't interact with my body in any meaningful way. Okay, but gravitons. Before I go on, and I say we, before I go on another tangent, gravitons. But first, I need to find a specific image, and I'm going to use the fact that I think I know what slide number it's on, but I need the slide on screen. So let's just put up CMB for no particular reason, and it should be slide 18. Yes, haha, the one that I have memorized. Okay, so this is the standard model of particle physics. These are the building blocks of nature. Excellent question about Higgs. We'll get to that in a sec. So these are the building blocks of normal matter. So this does not include dark matter or dark energy for now. This is just normal matter, which is everything we see, everything we're accustomed to, me, my tea mug, the stars, all of this is normal matter. Normal matter is made up of these 17 building blocks. So these are divided into two main families. We have the fermions and the bosons. The fermions are the building blocks, and the bosons are the ones that tell us how these building blocks can fit together. They're like the rules of the game. So within fermions, we have quarks. There are 6 of those. We have up, down, charm, strange, top, bottom, previously known as truth and beauty, changed to top, bottom for reasons. Who doesn't love a good top and bottom? So we have the 6 quarks, up, down, charm, strange, top, bottom. Now, the interesting thing about quarks, or quarks, depending on your pronunciation, is that these cannot be found alone. You always have multiple quarks together. So you can never find just one up. You always have like ups and downs, or chimes and strains, or charm and anti-charm, but you never find just one quark. They always bound up together. Then you have the leptons. Leptons can be found individually. Leptons, we have electrons, muon, and tau, and then there are neutrinos that I've talked about a bit already today, which are the electron neutrino, the muon neutrino, and the tau neutrino. So these are the 12 building blocks that make up matter. But then there's a question of how do these different particles talk to each other? And for that, we need the bosons. Now, the bosons are the ones that regulate the interactions between particles. We have the gluon. The gluon is the one that carries the strong force. It glues things together. This holds neutrons together with protons in atoms. It holds nucleus together. Then we have photons. Photons mediate or carry the electromagnetic force, electricity, and magnetism. Anytime you turn on a light or you use a fridge magnet or anything like that, you are using photons. You are exchanging photons. Then we have the Z and W bosons. The Z and W bosons are the ones that carry the weak nuclear force. So these are involved anytime you have radioactive decay or anytime you have neutrinos doing something fun, you're going to have these two bosons involved. And then we have the Higgs boson. Now, the Higgs boson is the one responsible for giving everything else mass. Without the Higgs boson, nothing would have mass. At some point in the very early universe, the Higgs boson turned on, and it's this treacle that fills space-time. So anytime a particle is moving through space-time, it has to overcome this treacle or this resistance, and this is the Higgs field, and we interpret this as being the particle's mass. So we have all of these here. Just going to answer questions before I go into where's gravity? Coffee is more popular in South India. I have heard that, and I was quite far to the north. And that was not in any way meant as a criticism. It was just I was craving coffee, but I found coffee, and that's fine. I'm sure hardcore conservatives get mad that the 2 quarks are called top and bottom. Well, they get mad at so many things, hard to keep up. Can one quark transmute into another? This is a great question. The answer is no, in principle. Ups and downs will stay ups and downs unless you have some type of reaction where you can bind together ups and downs and produce something else. But technically, these will not change. The top is a top, but up is an up, but down is a down, strange is a strange, and so on. Neutrinos, on the other hand, can change family. You can go from an electron to a muon to a tau, and back to a muon neutrino, and back to an electron, and electron to tau, and so on. The neutrinos can change between the different ones. The others do not. Okay. So this is the standard model of particle physics. But there are four forces that govern the universe. We have the strong nuclear force, we have the weak nuclear force, we have electromagnetic force, and we have gravity. I drop pen falls down, we stay in orbit around the sun, the moon stays in orbit around us, we get cool things like eclipses. This is gravity. And I mentioned all the other forces here. We have strong force with the gluon, we have electromagnetic force with the photon, we have weak force with W and Z bosons. Where is gravity? And this is the excellent question. And we actually don't know how to put gravity into this picture, because gravity explains how the world works on really, really large scales. This standard model of particle physics explains how the world works on quantum level. And putting these two together requires a theory of quantum gravity. We don't yet have one that works. It's very difficult because the energy scales involved are different, the length scales involved are vastly different. Putting these together is something that we haven't figured out how to do yet. But you could argue that based on how everything else looks, there should be another particle. Maybe there's another particle that carries a gravitational force. And this would be the graviton. Now, we have not found the graviton yet, but we could have a graviton. Now, a graviton would be this particle that is responsible for carrying the gravitational force. There's some things we do know about the graviton. If it exists, it would have to be massless. Why? Because gravity travels at the speed of light. We know this thanks to measurements of gravitational waves, and it's a prediction of Einstein's general relativity. So gravity travels at the speed of light, which means if it does have a particle that carries it, this particle has to be massless, like photons are massless. Just going to see if I can remove the spam comment that we got coming in here from Twitch. Yes. Okay, should have just removed that. I just got a spam comment. If you're on YouTube, you didn't see it. If you're on Twitch, you did. It's just one of those, bye followers. So just deleted that. It distracted me. It's deleted. So we have not yet found gravitons. We don't know if gravitons exist, and if they do, how we put them together into the standard model of particle physics. There are some limitations. We have an idea of how it should spin. We have an idea that it should be massless, but it's quite difficult to figure out if gravitons actually exist or not, because any type of experiment where you're looking for particles, you need to invoke quantum physics, and any type of experiment for gravity, we usually use gravity, Einstein's general relativity, and putting these together is something that we don't know how to do. So that is something that we are still trying to figure out. But then there's also the thing that, Einstein's general relativity is usually summarized in this very nice way of mass tells space-time how to bend, and space-time tells object how to move. Objects with mass will distort space-time, they produce a curvature of space-time, and then anything traveling through the universe will feel this curvature of space-time. So this is something that is kind of like a geometrical force, right? It's not really a particle, it's just the curvature of space-time. So how do we relate the curvature of space-time to a graviton? And this is a very difficult question. And depending on your perspective, you will either talk about gravity as being the curvature of space-time or as being a force. So Paul, you asked, your question here was, if gravitons turn out to be true, what would that mean? And the three options you listed, space is not curved. Now, based on a lot of experiments we've seen, space-time does have curvature. We interpret object with mass, the gravitational force, of being a curvature of space-time. This doesn't necessarily stop being the case if we find what causes this curvature at the quantum level. Option 2, gravitons operate within curved space. That could be. Or gravitons and curved space are just two different ways to explain the same phenomena of gravity. So that would be the one that I would go for. But it's very tricky, because until we actually figure out how to put gravity into this picture here, like how do we put gravity into the standard model of particle physics, until we figure this out, it's going to be quite hard to answer these questions. At some point, we might find a particle that behaves a lot like a graviton, and then we say, hey, look, we found a graviton. And then we'll add it to the standard model, potentially. And then we have a theory of quantum gravity, but we're not quite there yet. But it does seem to be the obvious question of how do we put gravity into this picture? Haven't figured that out before. Haven't figured that out yet, but maybe at some point. Related question from David here, David Howden. Did gravity exist before the Higgs field turned on? And I love this question. My answer is going to be yes. If we're thinking of gravity as being the curvature of space-time, then gravity has existed as long as space-time has existed, which means this predates the Higgs boson turning on. So we believe that in the very, very early universe, the four forces were actually united into one. Now, when we go to higher and higher energies, the forces can actually merge together. In the very early universe, we had very high temperatures. So we know that at some point, the electromagnetic force and the weak force were together in what is known as the electroweak force. If you can figure out how to put strong force into the mix, you get a grand unified theory. And if you can figure out how to join gravity in with the others, you get a theory of everything. We're not quite there yet, but this means that the four forces would kind of have appeared at the same time as all of the other particles appeared, which would be very early on. And basically, as soon as the universe starts, as soon as inflation ends and stuff starts happening, you have four forces, or maybe one, but you have what's going to be the equivalent of four forces today, to our knowledge. At some point, the Higgs boson turned on. Now, there is the very interesting question of, did the Higgs boson switching on cause the electromagnetic and the weak force to break away? Or did these two forces breaking away cause the Higgs boson to turn on? Or are these disconnected events? Based on the energy, it seems that these happened at the same time. Which triggered which this is something people like myself are actually working on, and not directly, but this is something that we are looking at. So what's the proof that electromagnetic and weak forces were combined back then? We can recreate this in a lab, smashing particles together. We can see this, and this is something that theoretically we can see as well, that this should have happened. So there's something that we call the electroweak symmetry breaking, which is this time where the electromagnetic force and the weak forces broke away. And this is something that gives us an idea of how particles behaved in the early universe. And depending on how this happened, it might have left ripples in the fabric of the universe in the form of gravitational waves. And I'm working on getting ready to find these someday with a space-based mission that we are launching in 10 years. So what is the proof that electromagnetic and weak forces were combined back then? I think the answer to that would be because it's something that we can kind of recreate in very high energy environments, and it's something that we theoretically need in order to explain how things looked in the early universe. But I feel like that answer is not complete. There's something missing to that answer there. Okay, sticking with this, I'm glad I could answer your question, Paul. Let's keep with these graviton questions. Question from Prathia: what if space curvature is how gravitons express themselves in the way that photons express themselves as light and magnetism? This might be, but then what is the mechanism here? How does a graviton cause curvature? What is happening here? Like we can kind of understand how photons produce electricity, or how photons are involved in magnetism. This is something we can understand, we can explain. Whereas, it's to do with electrons moving in different metals or in different materials. But how do gravitons curve space-time? Is the curvature of space-time just due to gravitons? And then there's the other fun thing that when you accelerate through space-time, imagine you're traveling in a rocket that is accelerating, you kind of feel the same effects as you would if space-time were curved. So even though there's no curvature, you feel that. So then there's a question of, would that also invoke gravitons? So these are questions that we don't directly have answers to because we don't know how to put gravity into this standard model of particle physics. So it's something that is very interesting, but something that we don't have an answer to yet. There are a lot of people working on this. For example, string theory, this idea that if you break down all of these particles, everything is made of strings that vibrate at different frequencies. And these vibrations give rise to all of the properties that we see. This is something that is an attempt to unite the quantum world and the gravitational world. So string theory is a realization of quantum gravity. Unfortunately, string theory doesn't seem to describe our universe. So in order to work, string theory needs more dimensions than we think we have. Okay, there was another question here. I hope I didn't miss questions, but going back to, there was the question here. What if black holes are made from graviton particles? And this is a great question. So black holes are objects in the universe that are extremely dense and massive. And they have such a strong gravitational pull that nothing can escape, not even light. In order to escape the gravitational pull of a black hole, you'd have to travel faster than light in a vacuum. And nothing, to our knowledge, can travel faster than light in a vacuum, therefore nothing can escape a black hole. So a black hole is really a region that has a huge gravitational pull. If gravitons really do exist, then they are going to play a big role in black holes. Black holes are going to intrinsically have gravitons if gravitons exist, because we define black holes basically as a gravitational object. It's an object that produces a huge distortion of space-time. If this huge distortion of space-time turns out to be a consequence of gravitons, then in order to talk about black holes, we'll have to incorporate gravitons. So if at some point we find gravitons, it's something that we will need to be able to fit in with things like black holes. And this is one of the reasons it's so difficult, because the scales that we're talking on are vastly different, right? These particles that I mentioned here, these are the ones that are the subatomic particles. A black hole is a massive object. And then there's also the thing that, we know by now, or pretty sure by now, that gravity travels at the speed of light. So this means that gravitons, if they exist, have to be massless. If you want a black hole to be entirely made of gravitons, then there's the question of, where does the black hole's mass come from? Or does it even have mass, or are we just measuring the curvature of space-time and implying a mass that might... Yeah, it gets complicated. We don't know how to put these two together. And it's not something that I am working on personally, but it is something that a lot of people are working on, because it's kind of like, it's the missing piece. Like, how do we put stuff here? There's also some, like, this is a very nice picture. It is by no means complete. This doesn't include dark matter. It doesn't include dark energy. And there's also the fun thing that everything here has mass, except photons and gluons. But we know that everything gets mass by talking to the Higgs boson. Neutrinos don't seem to talk to the Higgs boson. So how do neutrinos have mass? We have no idea. Why do neutrinos have mass? We have no idea. They do. But that's not a satisfying answer. So this picture is not complete. There are issues. And some people would argue that the lack of a graviton is an issue. Other people say it's fine, and gravity is just curvature of space-time, so we don't need to worry about it. So it's kind of very cool. Okay, a few more follow-ups. I see there's a lot of questions to this topic, which is good, because it's a very fun topic, very much above my pay grade, not what I was expecting to talk about today, but it's a super fun topic. But this is the thing, I come here like, let's see what we talk about. Okay, comment by Prath here. Like the way a gluon holds quarks together, the same way one part of space emits gravitons to attract other parts of space to itself. Yeah, I mean, it could be, right? This is the thing, that until we get a theory of quantum gravity, we can throw around ideas and we can discuss, like, what if gravitons do this? What if they do that? There are some experiments that limits what we can do with gravitons, but how we actually understand the graviton is something that is still very much not completely intuitive, especially not to me. I don't find gravitons in any way intuitive. I don't find gravity in any way intuitive. Like, why does space-time curve? Because it does. Why do objects with mass curve space-time? We can describe it mathematically, but why? I think this is something that is always slightly unsatisfying to me. Why is there not a graviton? Why have we not found it yet? Yes, a very cool topic, but not one that I'm in any way an expert on. Just making clear that, just stating that again, so that anything I say here, bear in mind, disclaimer, I'm not an expert on this. Is there anything to Interstellar's concept that you need to see inside a black hole to get the necessary parameters to unify relativity and quantum? I mean, it would give us more information, right? Is it the only way of going about it? Probably not. Are we going to jump into a black hole and magically teleport to a bookcase 50 years ago where we can solve all of humanity's problems and solve quantum gravity? Yeah, I was on board with Interstellar up until that point, Up until then, I loved Interstellar, and then the bookcasing. I've just spoiled the ending. Spoilers, like 10 years late, but yeah. So, do you need to go into a black hole to understand quantum gravity? Probably not. Would that help us? Potentially, if we could get any information back from inside the black hole, which we can't do. Because in order to get any information back from inside a black hole, we'd have to travel faster than light in a vacuum, which we can't do. And I just see there's a disclaimer to your comment that I didn't read. The follow-up comment, I don't mean can we see inside, I just mean is reasonable that knowledge is that what you would need to reconcile the two theories. So if you jump into a black hole, we don't know what happens. Could that black hole contain the necessary information to solve quantum gravity? It could, maybe. It could also contain space dragons. I mean, it probably doesn't, but it could. So if you jump into a black hole and you're not in the process of being spaghettified, maybe you would gain some deep insight into quantum gravity. Not sure what you would do with that insight because you've thrown yourself into a black hole and, trade-off. But it could provide more information because a black hole is one of the best places to test different ideas of gravity because it is such a big gravitational object. It's why a lot of times when people want to test modified gravity, so ideas where you modify Einstein's general relativity, the places we look are either cosmic voids, where there's basically no gravitational force, or overdense regions like at the center of galaxies where there's a lot of gravity, because then you have the extreme cases, right? And those are the ones that give you often the most information. Okay, if gravitons exist, I love all the graviton questions. Yeah, I see there's still quite a few more coming. Okay, more graviton questions. If gravitons exist, does that mean they can get out of a black hole to let its mass cause gravity outside? Yeah, see, this is a key question here because nothing can escape a black hole. You'd have to travel faster than light in order to escape a black hole. How would a graviton work? So then the idea here is gravitons would be massless, traveling at the speed of light, but they would not be able to escape the gravitational pull of a black hole. So then we're saying that the gravitons themselves are not inside the black hole, but rather around it, on the surface of it, escaping it. This is one of the reasons why it's so difficult to put these two together, because we notice the effects of a gravitational object, like big massive object curves space-time. This happens regardless of, it seems to happen regardless of whether it's a black hole or any massive object. So then, in order to explain gravitons or how gravitons work, if you want gravitons to be the ones responsible for this effect, you need a mechanism that allows gravitons to act in extreme cases like black holes, where they technically wouldn't be able to escape the event horizon. And the question you ask is a great question, and it's one that I can't answer, and I don't think anyone can answer this question, David Houghton, what would a graviton do inside a black hole? How would a graviton produce a curvature of space-time? If we could answer that, we'd be closer to having this idea of quantum gravity. So a lot of these questions that you were asking are great questions, and they're the questions that people are asking themselves, and they're the questions that we can't really answer. Okay, finish my infusion. This one, I don't mind if this one gets cold because it's quite a mild infusion. Okay, there was a comment here by Prath about W and Z bosons aren't massless. Let me just bring this up again. Standard model of particle physics. You'll see that in every block here, there are three numbers in the top left. These numbers are the mass, the charge, and the spin. So you go top to bottom, you have mass, charge, spin. So this gives you an idea. The spin is basically, imagine a particle that is spinning, except imagine a ball that is spinning. It's not a ball, it doesn't spin. It's just a quantum property. Spin is difficult to explain. Charge is the electrical charge of a particle. This also tells you if it talks to the electromagnetic force or not, so to speak, and how you can put these particles together. But the top left number in each box is the mass. So you can see Higgs boson has a mass of like 126 GeV over c squared. This is just some arbitrary units. You can see in top left they will have mass except gluon and photon. These are the massless ones. The Z boson and the W boson do have mass. And this is very, very cool because when we talk about this electroweak breaking and kind of the W and the Z bosons getting mass with the Higgs boson turning on, this is where a lot of cool physics is hidden. So yes, W and Z bosons do in fact have mass, which is very cool. That was a quick question, easy to answer that one. Okay, into a lot more gravitons. Ooh, gonna need a drink before moving into more gravitons. This is such a cool topic and a topic that I'm definitely not well versed in. Okay, question here. If the gravity field is part of the space-time fabric, perhaps the graviton particle is space-time folded upon itself if this is the case, then the graviton could be swallow light and collect mass on its surface. Then the question again is, but how? How does it do these things? What would it mean to have space-time folded upon itself? What would this look like? And is the gravity field actually part of space-time fabric, or does it just live in space-time? The other forces are not part of space-time, they live in space-time, the same as all of the particles. So then why would gravity be different? And actually, I kind of get the impression here that you're saying that gravity is an intrinsic property of space-time, which would make sense given that gravity is the curvature of space-time. But then how? How do we put this together? This is a big question. Comment from Ben here. In order to find graviton particles, would CERN need to reach Big Bang temperatures of 1 octillion degrees? So I don't think we'd be able to produce gravitons at the Large Hadron Collider because we can't go to high enough energies. And there's also the thing of like, how do you produce a graviton? Well, what is a graviton? We need to know what it is before we can produce it. So then we again come to the question of what properties of a graviton would we be looking for? When we find other particles at the Large Hadron Collider, where we smash bosons together, we see what comes out. Usually you know what type of signature to look for. You know, you're looking for something that produces a light in this detector or something that carries mass over here. So this is something that you know what to expect, but what would a graviton look like in a detector? How would we measure this? We don't know because we don't know what a graviton is. So yeah, all of these questions come back to the idea of we need a theory of quantum gravity, and then we can try to answer all of these questions. Comment from Paul, preface with weird, love that. If gravitons are being emitted from the surface of a black hole, then maybe negative gravitons are plunging in from the surface to balance it out. What is a negative graviton? How does a negative graviton behave? Are you talking about an anti-graviton here? Now, a lot of these particles can have anti-particles. You can have an up, you can have an anti-up. These are particles that have very similar properties but opposite charge. So if you have, for example, an electron and an anti-electron, these come together, they annihilate. Gluons, photons don't have antiparticles. Higgs boson probably doesn't have an antiparticle. Z boson, W bosons, there you can probably have antiparticles, but what would an anti-graviton look like? What would that even mean? What would it be? What would its properties be? Now, technically, we think that a graviton would have spin 2, I think it is spin 2, maybe? Yes, spin 2. So what would that even look like in terms of constructing an anti-graviton? What would an anti-graviton or a graviton have charge? Probably not, but again, these are questions. I'm sure there are people who work on quantum gravity who actually have answers to some of these questions. I am not one of those people, but I feel like there are probably some answers out there towards what gravitons are, or some ideas or some hypotheses, or like it can't do this because. But until we figure out, are gravitons real? What do they do? What do they behave like? How do we explain the curvature of space-time via a particle? Until we can answer this, a lot of these questions you're all asking are great questions. And a lot of the ideas you're discussing are very cool ideas. But they're ones that we come back to the core thing of how do you put the curvature of space-time together with a particle? How do you explain these? Are they the same thing just viewed from, are they two sides of the same coin? You know, are we just using different words to explain the same thing? A graviton would be its own antiparticle. If it has antiparticles, it would be its own antiparticle. Does it have an antiparticle? Is there an antigraviton? Your thesis, first thesis, gravitons only emit gravity. They aren't affected by gravity, so they can escape a black hole. So the idea here is that gravitons produce the gravity, but they don't feel the gravity. But then the question again is, how? How does this work? I mean, I can give you the example going back to the standard model of particle physics here. We have the Higgs boson here, top right. Now, the Higgs boson is the one that gives everything else mass, but it also has mass itself. It kind of creates this field, this treacle that all the particles have to navigate, including itself. So the Higgs boson is not really emitting mass-giving particles. It is the mass-giving particle. It produces this field, and it feels the field itself as well. So your idea here, Prath, is to have a graviton that produces the gravitational effect but doesn't feel the gravitational effect itself. So then the question is, how are we producing a gravitational field? And if so, why don't the ones producing the gravitational field feel the gravitational field? We come back to the idea of we don't know. They're all great ideas, and I love that you're brainstorming. We're going to solve quantum gravity in this live stream. This is where we solve it. I write it up tomorrow. I love that you're brainstorming ideas, and everything you're coming up with is reasonable. But we come back to the idea of we just can put these together on the most fundamental level. We haven't figured out how to yet. Comment from Poop here. I've been seeing a lot of talk about locality. How does it tie in with cosmology and the Hubble tension? Love this question. So locality is the idea of laws happening locally in one place. Are they global laws? Are they local laws? That was a very bad answer there. So locality is really about, does the location in which you do an experiment affect the results or affect the laws that you're studying? That is something that is a big question in cosmology. It's something that has been tested. How does that fit in with the Hubble tension? I'm going to leave that question because I am planning a whole conversation soon, a whole stream soon about the Hubble tension. Very briefly, the Hubble tension is what you get when you try to measure how fast the universe is expanding. So we know that the universe is expanding. We know that the universe is expanding faster today than it was in the past. However, there are several different ways we can go about trying to figure out how quickly the universe is expanding. And depending on how you ask this question, you get different answers. So one of the ways you can ask this is by looking at local close by objects like supernova that are exploding stars in close by galaxies. You can use that to get an idea of distances, and then you can see how these distances change as you go further out. And then you can get an idea of the acceleration. Another way we can measure how quickly space-time is expanding is by using the cosmic microwave background radiation. It had to come back before the end of the stream. You can use this earliest light in the universe, project it forward, assuming a cosmological model, and then ask a question of how quickly is the universe expanding. And if you do these two different things, you could get vastly different numbers. You could get 50 and 3,000, but you get numbers that are really, really close. One value, the CMB gives you 67, supernova gives you 74, which are very, very, very close, but not close enough because these numbers have very good precision and they are too far away for comfort. This is known as the Hubble tension, Hubble crisis, depending on who you ask. It's something that I think is extremely fascinating. It's something I've worked on. I think it's very cool. There may have been a recent development. So there was a conference this week even, that was like closed doors officially. It was for registered participants only. And apparently there was an announcement there that there might have been a development in the Hubble tension, but this has not yet been written up in a paper and it's not yet been peer reviewed. So this is something that we're kind of now just like, a screenshot of a plot taken from a talk is not enough to claim anything. And that's why I'm not saying who's found what or who's claimed what. But I'm going to do a whole stream about the Hubble tension soon, review the current status and what's happening. And maybe by the time I do that, there will be an update. We'll see. This has already been reported in Nature. This is not anything super confidential that I'm telling you here, because there was a journalist from Nature there. This has already been written up, but it's still everyone's kind of like, I need to see the paper. Paparazzi science, a screenshot snuck from the back row of a talk. Yeah, so at some point there's a rumor of something that happened years ago that seems to actually have happened, where results were presented at a conference without being published, and someone took a photo of the plot and then used that photo to reproduce the results and actually published it before the authors did. This is often why in conferences anything that is preliminary has a big preliminary badge thrown on top. So paparazzi science is not the way we do science. We want peer review. We want to read the whole paper, and I don't agree with spreading rumors within science, and I'm very much not trying to spread a rumor. Just it looks like there could have been a development. As soon as there is confirmation or anything public of this, I'm going to go into detail about it. So that is a stream that is going to happen soon, also because I love talking about the Hubble tension. Okay, 2 more questions, and then we're going to wrap up because we are almost at the 1 hour mark. I know we did a lot of tangents today. There was a tangent about tea. There was a tangent about costume parties. So we did take some tangents, but we got to gravitons, and gravitons are cool. So maybe fundamental laws change depending on the density of the universe. Maybe. This is something we have tried to test, and so far we haven't found any changing of a fundamental law. So that's fun. But maybe it's something that people are looking into. Comment from Prath is that if a negative graviton could stand for anti-gravity, that there should be an anti-photon that represents negative energy. But as far as I know, it is not possible. Indeed, photons do not have antiparticles. There is no such thing as an antiphoton. But could there be an anti-graviton? Depends on the properties of a graviton. What properties does a graviton have? We'll know when we figure out quantum gravity. When's that going to be? Well, you all have some great ideas. So maybe this is the seed that's been planted for a theory of quantum gravity. You heard it here first, guys. Someone's going to read these comments and be like, actually, let's go with that. So if anyone does that, if anyone comes and reads these comments and gets inspired for quantum gravity, please do cite Cup of Cosmology and whoever made the comment that promoted this idea. Maybe someday it would be very cool if like quantum gravity solved in a YouTube live stream. That would be very funny. But probably not going to happen today. But it is very, very interesting. And if there is a lot of interest in this topic, I could try to get somebody who works on quantum gravity to join Cup of Cosmology and do this properly. A couple of names come to mind. I'll see if people are interested in a whole stream about quantum gravity done with someone who actually works on quantum gravity. I'll see what I can do. I'll see if I can get someone to do that. I'm sure there's someone out there who would be happy to do that. Okay, I think I addressed all of the comments, or at least acknowledged all of the comments. Any geniuses watching have full permission to use my random ramblings as seeds to their idea. Okay, Paul has given you permission. If Paul has the idea for quantum gravity here, go ahead, write it up, let us know. We look forward to seeing this. So I think I got through all of the questions, hopefully, or at least acknowledged all of the comments. If not, please don't take it personally. There's often a lot of comments. I was jumping around a lot from comment to comment. So if I ignored your comment, it was not intentional. Feel free to post it again. And as always, you can reach out to me via the email address that is contact@cupofcosmology.com. You are all welcome to follow me on Mastodon. That is dchooper91_Cosmo on the astrodon.social server. And my DMs are open on that Mastodon for now. You are always welcome to send me messages. You are welcome to send me emails. As always, I don't necessarily reply to emails quickly, but I do try to reply eventually. Or I just move into a folder saying never replied, and that's the end of the email. I think talking about gravitons today gives you some idea about how enthusiastic you are about quantum gravity. Yeah, I'm going to add that to the list of topics I want to do in depth. I'm actually making a note of it. There's nobody to my knowledge is there someone in my group who could do that? I will see. I'll see what I can do. No promises, but I'll see if I can get a quantum gravity expert on Cup of Cosmology, because that would be very fun. You heard it here first. Unified theory of universe in next week's Cup of Cosmology. Let's see. So just a reminder, I have 3 streams coming up. Not yet clear on the exact dates. Yeah, you never got an email back from me, Scott. That email moved to the folder of never answered, and it stayed there. So it's out of sight, out of mind. Feel free to follow up on that if you want, if the question is still relevant. I read it, I was like, yeah, I'll answer, and then never did. I'm aware of that, but now it's out of the inbox, so don't expect a reply anytime soon. Okay, so at some point soon, very soon, I'm going to do a stream entirely about neutrinos, what neutrinos are, why they're called for cosmology. This will either be next Sunday or the week after, because as I mentioned at the beginning of the stream, I might have plans next Sunday. Still not completely sure. I might have plans next Sunday, in which case I wouldn't do a stream. But then technically, either next Sunday or the one after, there will be a stream about neutrinos. The reason for this is because I'm attending Neutrinos from Home, which is a very cool online conference dedicated entirely to neutrinos. I'm expecting to learn a lot of cool stuff. And then I'm expecting to just come and share all of the cool stuff with you. There might be some conference-related outreach event. I will promote it if that's happening. I will promote it on my Mastodon. And I'm not sure where else, but follow me on Mastodon for those updates. And then at some point soon, I'm going to do a stream about Hubble tension for reasons that may or may not become clear over the next couple of weeks. And then at some point, I want to do a stream about ups and downs of academia, the truth, the ugly, the bad, and everything in between. And it's going to be an honest discussion prompted by some recent turmoil in my own life. But that's also a stream that is coming soon when I'm in the right mindset, because that's going to be a fun one. Bring your popcorn for that one. That's going to be a fun one. Just comment in general. I am very happy in academia right now, but I think it's good to talk about the things that people don't often talk about in academia. So those 3 streams are coming up soon. Not exactly sure when. As I mentioned before, next Sunday, still not completely clear if I will be doing a live stream, but you can subscribe to the channel to be notified. As I said at the beginning of the stream, I always schedule the live streams about at least 6 hours in advance. So if you're not sure if I'm online at any point within 6 hours before my stream is due to start, just check the Cup of Cosmology YouTube channel and you'll see if there's a stream scheduled or not. Subscribe to be notified when I go live. Like the video, leave a comment. You know how YouTube works. Do all of the stuff, press buttons, make stuff happen. Whew, okay. That was a super fun conversation today. I feel like I was not prepared for a conversation on quantum gravity, but we did it anyway, and it was super fun. And I love all of the ideas and all of the interest. We also had some fun tangents about tea and about conferences and about costume parties. Lots of fun tangents and lots of very fun conversations about gravitons. So as always, thank you everyone for joining. This has been really, really fun. Cup of Cosmology should be online either next week or the week after. I hope to see you all again then. And I hope in the meantime you all stay safe and take care of each other.